Hi there. In this video, we'll take a look at the second major topic in calculus, which involves figuring out the distance that an object has traveled when you know its velocity. Okay, this is taken from page 270 in the book, and what I did was I took the problem set with problems 1 through 4, and I modified them for the purpose of this video. Alright, so this video should help you with that homework set if you need any assistance. Okay, so problem 1 just starts out real simple. A particle starts at position x equals 0. It's moving along the x-axis, so in a straight line, with the velocity 3, we'll say miles per hour, for t greater than 0. Where is that darn particle at t equals 5? Well, let's actually watch the particle move for a moment here. So, again, we're given that the velocity is 3, we'll say miles per hour, and let's just watch it move for a moment. So in 1 second, you would expect it to go 3 miles. In 2 hours, you'd expect it to go 6 miles. 3 hours, 9 miles, etc. Okay, and what we'll do here is we'll just make a sketch of the information that we have. So again, we just want to know where it is at t equals 5. So let's put a mark down accordingly. 0, 1, 2, 3 hours, 4 hours, 5 hours. And the whole time, the thing is moving at 3 miles per hour. So that's true just during the entire journey. It's moving 3 miles per hour. So not a very exciting graph, but it's perfect to illustrate the main point of this section and of this entire sequence of lessons about integral calculus. So in particular, it makes sense that if you travel for 5 hours at 3 miles per hour, it stands to reason that the total distance you traveled is simply 15 miles. Okay, in particular, notice that we took the width of the rectangle, which was 5, and the height of the rectangle, which was 3. We multiplied them together, and that produces a number which represents the area of this region. Okay, and maybe I can do this a little better here. In 1 hour, we went 3, 6, 9, 12. Can we even just like make this real pretty so that it's obvious what's going on with this? Let me make some room for this. Let me make it super obvious what's happening with this graph. So here's 1 hour, 2 hours, 3 hours, 4 hours, 5, and 1 mile per hour, 2 miles per hour, 3 miles per hour. There you can see clearly that there are 15 boxes. So what does each box represent? 1 hour, 1 mile per hour, you went 1 mile, 2 miles, 3 miles. Altogether, you traveled 15 miles. Okay, so there's a visual that just captures the main point of the lesson. We get the area under a graph, and if we do the area on a velocity graph, then that area represents a distance traveled. Okay, so solution, where is the particle? It's at position 15. X equals 15 miles. Alright, so that was just a very simple problem because the velocity was constant. In problem 2, now we're given something a little more exciting. This time the velocity varies according to time, according to the formula 3t plus 2. So let's pop over to Sketchpad and watch how this particle moves. Alright, so just to get a feel for this, let's go up to 1 second. At 1 second, we get 3 times 1 plus 2, which is 5. And the position is at 3.5, apparently. If we go to 2 seconds, we get 3 times 2, which is 6, plus 2, which is 8. So it's now going 8 miles per hour, and it's moved 10 miles altogether during those 2 seconds. And let's watch this just for a second. And do you notice that the particle is not moving at a constant speed? It's like speeding up. So it's like slow, fast. Okay, so that makes it a little more interesting. Okay, let's get our velocity time graph and see if we can estimate or compute the distance that it traveled. Okay, so this time we're going to pay attention to a 4-second time interval. I'm kind of freely switching between seconds and hours here. I hope that doesn't bother anybody. Feet per second, miles per hour, whatever makes your day. Okay, so let's see. If I plug in 0 into this formula, I'm getting 3 times 0 plus 2, which gives 2. If I plug in 1, you get 3 times 1 plus 2, which gives 5. When t equals 2, you get 6 plus 2, that's 8. When t is 3, you get 9 plus 2, that's 11. And when t equals 4, whoops, giant eraser there. When t equals 4, we get 12 and 2, that makes 14, somewhere up here. Okay, and so our velocity graph looks like a straight line. Okay, now if you're willing to believe that these rectangles, which represented an area, which represented a distance, if you're willing to believe still that the entire area, even though it's no longer rectangular, that it still represents the distance, then we should be able to find the distance traveled by computing this area right here. All right, so let's see if we can do that. Well, what are we dealing with? Well, this is just a trapezoid. Okay, the height of the trapezoid is 2 on this side. It's 4 on this side. Can we just make this easy? Forget trapezoids. Let's just deal with a rectangle and a triangle. All right, so here goes. The rectangle has height 2 and width 4, so its area is 8. And let's see, this was 14 altogether. I've already used 2, so there's 12 more right there. So we've got a 12 by 4 triangle. It's 48. Half 48 is 24. So the area of the triangle is 24, and therefore the total area is 32. Okay, so we would estimate if the particle is moving this many, let's just say feet per second for variety, then we would estimate that in 4 seconds it would move 32 feet. And let's check in with the sketch pad and see if that agrees with what we see. All right, so I'm going to back this up. Is it true that in 4 seconds we move 32 feet? Let's find out. Here's 4 seconds. And let's pop over and watch our particle. And there it is, right there at the 32-foot marker. Okay, so our math agrees with our software. And in a moment, we'll take a look at this more complex problem. Okay, so with this example, we're looking at something that is quite a bit more complicated, as we'll see. But same basic storyline. We've got a particle moving in a straight line. Starts out at the origin. And we know its velocity. So if you like, you can visualize. We know the speedometer. We know what's going on with the speedometer at any given time. And that allows us to figure out what goes on with the odometer using our calculus skills. Okay, so here goes. Let me just go ahead and reset this board. And so what we're going to do is try to construct the graph of this thing. We know that it's going to look like a parabola of some sort. And we're interested in a 2-second time interval. So let's set up our graph according to that. Okay, so let's just go ahead and plug in. If we do 0 squared plus 2, you get 3. If we do 1 squared plus 3, we get 4. So that's going to be 4 right there. If we do 2 squared plus 3, we're getting 4 plus 3, which is 7. So let's see, 3, 6, 7, somewhere around there. All right. And now we're in a position to simply sketch the velocity curve. Okay. And so this one is truly more difficult than the previous problems. First example was simply a rectangle. Just do base times height, easy. The second one, we had to be a little bit clever to compute the area, but a trapezoid is easy to break down. Now we have this parabola, and there just is no handy formula using our background knowledge from geometry there just isn't a handy formula for finding the area of a region that's bounded by a parabola. All right, so we're going to have to rely on approximation by rectangles, and that really is the point of this lesson. All right, so if I fit in enough rectangles under that curve, I should be able to compute their area and then add them up to get the area under this parabola. All right, let's see if we can get that done. Okay, I'm going to choose, for the purpose of this example, to use 5 rectangles. So n is in number of rectangles here. And I'm going to create them in such a way that they all have equal widths. All right, so really what I'm doing is I'm taking this 2-hour time window and I'm dividing it up into 5 little blocks. Okay, now let's think for a second here. If you take a 2-hour time window and divide it into 5 blocks, shouldn't each block be 2/5 of an hour? Okay, 2 hours divided into 5 blocks gives 2/5 of an hour, which is 4/10. Okay, so what I'm going to do now is I'm just going to go along my time axis. Let's get rid of 1. And let's break this up according to 4/10 of an hour. So we'll go 4/10, 8/10, keep adding 0.4 here, 1 and 2/10, 1 and 6/10, and then 20/10. So now we're up to 2. All right. And several ways we could proceed to make these rectangles. We could use the left endpoint of each interval and make a rectangle. Let me just draw what that would look like. Left rectangle, left rectangle. All right, now I'm on this subinterval. Let me go to the left endpoint, make a rectangle. Go to the left endpoint, make a rectangle. And if you do it that way, it's clear that the area that you would get is going to be too low. In particular, we're leaving this region out, so we would expect to get an underestimate. All right, and let me just illustrate some of our other options. Okay, so within each little subinterval here, we could instead choose the right endpoint and make a rectangle around that. Right endpoint. Now I'm on here, right endpoint. Within here, right endpoint, right endpoint. All right, and this time we're getting all the area we need plus more. All right, so in particular, we are getting this much additional area, which we didn't want to count. So if you did it this way for this example, you would expect to get an overestimate for the actual area. A third option is simply to use the midpoint. Maybe that in some sense splits the difference. So within each subinterval here, we could choose the midpoint, 0.2, go up to the curve, make a rectangle. 0.6, up to the curve, make a rectangle. All right, let me do this in a way that's going to be visually clearer. All right, so I'm just using these midpoints. I'll make a mark at the midpoint of each subinterval. And rather than trace it, I'll just make a mark here. Rectangle. Height. Okay, the height of the rectangle is determined by the midpoint. The height of the curve at the midpoint of the subinterval. Height of the curve. Midpoint of subinterval. Height of the curve at the midpoint of the subinterval. Okay, and this time we're sort of in an in-between situation. For each of the rectangles, we get a little bit that we don't want, and we miss a little bit that we do want. Maybe in some sense those cancel out, although we wouldn't expect them to exactly cancel necessarily, or we shouldn't assume that they do. Okay, so 3 different options. We have approximation by left endpoint rectangles. That's called LRAM, left rectangular approximation method. We could use approximation by right endpoint rectangles, which is called RRAM, right rectangular approximation method. Or we could split the difference and do an approximation using the midpoint of each subinterval, which is known as MRAM, midpoint rectangular approximation method. In fact, you could even use a random point within each subinterval, as we'll see. All right, so these are just some convenient choices. For purposes of the example going forward, I'm going to use midpoints, knowing that that's what they do that's the expectation in the homework set, so I'll just go with that. Okay, So now it remains to actually calculate the area of each of these 5 rectangles. Okay, and so let me shrink this down and clean up my workspace so that I can do that. Let's see here. So I've got my rectangle set up. We know that where that's coming from. Whoops, too much. Can I delete just only this much, please? Boom. Okay. No, too much. So I'm just going to shrink this down at this point and give myself some room to do some computation. All right, so velocity and time are going to go. See ya. Okie doke. So within each rectangle, we need to apply the basic formula for the area of a rectangle. Why am I on yellow here? Which is base times height. Okay. And can I just select one of these for purposes of illustration here? Why don't I show how I'm computing the area of that 4th rectangle specifically? Okay. Well, the base of it is the difference between 1.6 and 1.2, which is 4/10. And that looks familiar because that's just the 2 hours divided 5 times, and that's how we got 4/10. All right, so the base of the rectangle, and each rectangle, actually, is 4/10. How high is that rectangle? How tall is it? Well, how did we get its height? We got its height by using the velocity formula, which was given to us up here. Okay? And we simply selected the midpoint of this subinterval. So in between 1.2 and 1.6 is 1.4. And if we use 1.4 in this formula, we get this. And now it's appropriate to just like reach for a calculator and let it return an answer to you so we don't get caught up on the arithmetic. Okay, so 1.4 squared plus 3 is 4.96. And that's how high that rectangle is. When we multiply by 0.4, it returns an area of 1.984. Okay, so that basically illustrates the method. And now let's just perform that calculation for each of the 5 rectangles that are up here. All right, so I'm going to make some room for that. And maybe with less commentary, I can just do the computations. Okay, here goes. Okay, so little rectangle 1, I'm just going to be writing down the width times the height. And all of them have a width of 0.4, so maybe I'll just get that out of the way. Boom. The width is 0.4 for each rectangle. Only the heights vary. Okie doke. So let's see, the midpoint of the first subinterval was 0.2, so we'll do 0.2 squared plus 3. Again, I'm just using the formula that represents where the curve came from in the first place. Next, the midpoint of rectangle 2 is based around 0.6. Put that in the formula to get the height of the rectangle. Midpoint, 1.0. The midpoint of the next one is 1.4. That's the one I did a moment ago as an example. And the last subinterval has a midpoint of 1.8. And I'm just going to punch these into my calculator real quickly here and get some answers. 0.2 squared plus 3 times 0.4. I'm getting 1.216 here. Next one. Let's change that to 0.4 squared. I get 1.264. I like the fact that's a little bit bigger because this rectangle is a little larger than that, so that makes sense to me. Okay, change 0.4 to let's see, I think I typed that one in wrong. I'm going to have to do an error correction here. Correction. I was supposed to type in 0.6 there. Should be 1.344. All right, back on track. Let's change that to 1.0. 1.0. And I get 1.6 even. Okay, what about 1.4? I get 1.984. And lastly, we'll plug in 1.8, and we get 2.496. Okay. If we want to get an approximation for the total distance traveled, we just need to add these up. So let's see what that gives. 1.216 plus 1.344 plus 1.6 plus 1.984 plus 2.496. I'm getting 8.64. Okay, so what does it all mean? Well, let me shrink this down. Whoops, didn't mean to move that guy. Just want to shrink this down. So I have a little bit of room to talk. Okay, what does this mean? Well, it's our approximation on the basis of these 5 rectangles, which were determined using the midpoint method. Okay, and so we determined that the area under the parabola between t equals 0 and t equals 2 is approximately 8.64. So I'll write area under the curve Vt equals t squared plus 3 from t equals 0 to t equals 2 is approximately 8.64. And so what does that mean? Well, that's approximately how far the particle moved during that 2-second time interval. Okay? And let's at this point, let's now pop over to WinPlot, a more powerful software tool, certainly much more powerful than I am just doing these calculations by hand and using my calculator. All right. Let's get a visual confirmation for our work and also extend our work. So here goes. Notice this is simply the formula x squared plus 3, which is what we've been dealing with. We're starting at 0 and going up as high as 2. And let me make this match. So we did 5 rectangles. And let me just illustrate. So first we'll check our work. All right, using the midpoint rectangles, here are the 5 rectangles that I attempted to sketch. And there you see that the computer is computing 8.64. So that confirms that the work we did was correct. Yay. All right, but is that the true area? Is that really how far this particle traveled, 8.64 feet? Well, if we use more rectangles, let me kick that up to 10. Now we're getting a better approximation for the region. Why don't we just keep going with that for quite a while? You see what's happening here? By the time I get up to about 50 rectangles, man, that's an awfully good representation of the curve. But why not go to 100? Can we do 200? All right, by the time I type in 200 rectangles, the software program is just displaying the region at that point. All right, and the number isn't even changing anymore. So apparently the true area under this curve is somewhere around 8.66, etc. Okay. As I said, though, let's go a little further with this just to illustrate some concepts about integration. Reminder, the term integrate means put together. And the idea here is we're putting together all the areas of all these individual rectangles to make the whole region. All right. So what happens if, and I'll go back to 5 rectangles, what happens if we use left endpoints? Well, as we said earlier, we're missing some of the area that we wanted to count, so we're expecting 7.92 to be a little bit too small. But as we increase the number of rectangles, and again, I'll just go up to 150 here. Bam! As we increase the number of rectangles, we're getting closer and closer to that apparently true value of 8.666666. Okay, and in fact, you can see that that's still changing. Even with that many rectangles, it's still zooming in on the true value. Okay, how about I just go to right to 1,000? All right, Now we're 8.66, but it's still going. All right, but notice it's getting there from below in particular. What happens if I use right endpoint rectangles? And I'll reset that to 5. Well, as we saw earlier, now we're getting an excess amount of area, so this should be too big, and it is larger than 8.66. But again, as I increase the number of rectangles, we can get a better and better approximation for this region, and so the area should get closer to the true area. And again, let's just go right to 1,000 here. Let's do 2,000 rectangles. Be exciting. Okay. And we're still larger than 8.666666. And you can see it's still changing there, but slowly. All right, so it's zooming in on that same target, just this time from above rather than below. Okay, midpoint method. Starting at 5 rectangles again. Here's our answer, which we computed, 8.64. And I'm just going to increase the number of rectangles again. And you can see that's zooming in awfully quickly. Can I go right to 2,000 again? Let's do 3,000. Ooh. Okay. And there you see it's getting awfully close to the target value. It's not even changing. As I add rectangles, it's staying pretty constant. Okay. There's some other options here that we can perhaps explore in later lessons. Maybe I'll just do a quick snapshot of that. Besides rectangles, you can also use trapezoids to approximate a region. There's one trapezoid, there's two, and you can see the trapezoids are like really good. Even with just 6 trapezoids, it's pretty darn close to what the parabola looks like. All right, and by the time I do like 50 trapezoids, it's getting awfully close to that true value that we were expecting. Okay, parabolas themselves can be used to approximate regions. Okay, and you can even use like a random point. I think I mentioned earlier that I was going to comment on this. This approximation method is so good, it doesn't depend on using specifically the left endpoint or specifically the midpoint or specifically the right endpoint. You don't have to use any specific point. If you get a bunch of rectangles, you can actually use any point at all. So this is showing a random point within each subinterval, of which there's 5 right now. And notice some rectangles are like below, some parts are above, and as I increase this, you'll see it sort of jumping around in kind of a random fashion. And you might think, well, if they're random, like how does that work? That doesn't seem like it should work. Again, the idea is if you get enough rectangles, as the number of rectangles increases, the area is still going to approximate the true region. So again, if I do, let's just go right to 5,000 random rectangles, and you see right there, 8.6s forever. Okay, so I hope this video helps you to understand integration. And again, the big idea is that if you start with, we go back to title screen, if you start with, oops, that's not resetting, the velocity of a curve, you can use the area under the curve to find the distance the particle has traveled. All right, and big idea from over here is that as we use more and more rectangles, which are simple to compute areas for, we get a better and better approximation for the true area. Lastly, you might wonder, is there some way to calculate the area where I don't need software and where I don't need to use like 20 bazillion rectangles? And the answer to that question is upcoming in the course, so something to look forward to. Hope this video was helpful to you. See you next time.